finish going over the review today. Now, the first thing we're starting out is the rational zeros. We want to find all the rational zeros for these here. No, they just require you for English and mathematics to have a 19 to take college algebra. If you do not have a 19 essentially for college algebra and the college English classes, they make you take a remedial class first and then you can take it. So it's almost, you have to pay to take a course to get you ready for that course and then pay for it too. So that's why we try to get, why I say, especially get at least a 19 in math and English to avoid that class. No, it just means you need additional practice. Do we want to look at problem 25 or 26? Huh? 26? So when we look at the rational zeros theorem, we need to find the number of positive solutions and negative solutions. And when we find the number of positive solutions, no, sorry, I'm getting ahead of myself. Rational zeros is our plus or minus p over q, where p is the factors of the constant term and q is the factors of the leading coefficient. So the constant term, the term without x, in this case is 15. We're not worried about the sign, just the number itself. So the factors of 15 are 1 and 15 and 3 and 5. So these are our four factors of p, our factors of 15. Q is the factors of the leading coefficient, the number in front of the variable with the biggest exponent. So factors of 12. So we have 1 and 12, 2 and 6, and 3 and 4. Questions on how we found the factors of p and q? Questions on this here so far? Now the rational zeros, what we're going to do is divide every value of p by every value of q. And we start with 1. I think it's best to start with one value of q at a time. So the first thing we're going to do is to divide all the values of p by 1. We're going to put it over 1. So 1 divided by 1 is 1. 3 divided by 1 is 3. 5 divided by 1 is 5. And 15 divided by 1 is 15. So with any of our possible, or any one we do, we will relist the factors of p, which is plus and minus, because we're going to have to divide it by 1. No matter what the value of q is, 1 will always be one of its factors. Once we do that, then we'll move on to 2. Plus or minus, we'll do 1 over 2. 1 divided by 2 is 1/2. Then we can move on to plus or minus 3 over 2. 3 over 2 does not reduce. Then we can move on to plus or minus 5 over 2. And lastly, we have plus or minus 15 over 2. And any of these here, especially with the fractions, we can plug them in to the yellow calculator in that fractional form. And if we get the number back, it doesn't reduce. And if it hasn't already showed up once, we list it out. Questions on this so far? Now we're going to move on to 3. So we're going to say plus or minus 1 over 3. Our next one is 3. Well, what is 3 over 3? 3 over 3. 3 divided by 3. 3 over 3 is 1. Has 1 already been listed? Yeah. If it's already been listed, we don't list it again. So we can move on to 5 over 3. Well, 5 over 3 doesn't reduce, doesn't turn into anything else. And we don't have it so far, so we'll list out 5/3. And the last one's going to be 15 over 3, which is 5. Do we have 5? Yeah, so we don't have to list it again. Now we're going to move on to 4. Well, the only thing, the ones we haven't had to list, is if the numerator, our value of p and value of q, had a common factor, yes? Our next number is 4. Do 1, 3, 5, or 15, any of those have a common factor with 4? Well, no, all of them would have to be 2 of some kind. We don't have them. So we're end up going to just listing them all out, because we'll have 1 over, yeah, they do have 1, but that doesn't do much, unfortunately. Then we'll have plus or minus 3 over 4, and then plus or minus 5 over 4, and plus or minus 15 over 4. And if you're not sure that if it reduces or if it's been repeated, stick it into the calculator in fractional form and see if it does. Because if it does reduce, because you put it in, hit enter, and it reduced, it will reduce it down. If it doesn't, it'll just give you the fraction back. Then we can move on to 6. So we're going to say 1 over 6 would be plus or minus 1/6. Well, 3 over 6 reduces to 1/2. Do we have 1/2? The first one in green, so we have it. We don't have to list it again. 5 over 6 doesn't reduce, so we'll have plus or minus 5 over 6. Would 15 over 6 reduce? It does, to 5/2. Is 5/2 already listed? Yes, so we're done with that one. Lastly is 12. We'll have plus or minus 1/12. 3/12 if we plugged it in would reduce to 1/4. We do have it. 5/12 does not reduce, so plus or minus 5/12. And lastly, 15/12 would reduce to 5/4, which we do have. So these here are all of our rational zeros, all of our possible rational zeros for this function here. So if this polynomial, this higher degree polynomial equation has rational solutions, it's going to be one of these here. Questions on this here? This problem here, this is all it's asking for. It's just asking us to list them out. It's not asking us to solve this. And it actually turns out none of these rational zeros actually work for this function. So there's no solving it for us anyways. Questions on 25 and 26? We ready for 27 and 28? 27 and 28, use Descartes' rule of signs to find the possible number of positive, negative, complex zeros. Do we want to look at 27 or 28? Okay. So we look at 27. If we were solving it, the degree would tell us the number of solutions. Here the degree is 5, so there should be 5 solutions. Now to find the number of positive solutions, we count the number of sign changes of the function itself. So x to the 5th to x to the 4th goes from positive 2, so that's 1. 4th to the 3rd goes from negative 2 positive, so that's 2. From our 3rd to squared goes from positive 2 negative. From x squared to x goes to negative, the sign did not change, so we can't count it. And from x to our constant term, it changes one more time, telling us that there are 4 positive solutions, 4 possible positive solutions, or less than it by an even amount. So we could say 2 and 0 because we're just subtracting 2 from it. 4 minus 2 is 2, and if we subtract 2 again, we get 0. So out of our positive solutions, we could have 4 positive, 2 positive, or 0. One of those options there. For our negative case, f of negative x, and the total process for this here is we're plugging negative x in for every x in the entire equation. But at this point, what you really need to focus on for this here is we're going to rewrite the equation out. If the exponent is an odd number, if the exponent is an odd number, change the sign in front of the variable. If it's even, keep the sign the same. So our first one is 6x to the fifth. The fifth power is even or odd? Odd. 5's odd, so since it's an odd power, we change the sign. It was positive, means it's now going to be negative. The next power, next is 27x to the fourth. Is the exponent even or odd? So the sign stays the same. Since it was negative, it's going to stay negative. Our next one, 56x to the third. Is the exponent even or odd? Odd, so the sign would change from positive to negative. Our next one, x squared. The exponent is 2, so it is even. And if the exponent's even, the sign stays the same. Since it was negative, it's going to stay negative. Our next one is 36x. Since the exponent is not listed, it's understood to be 1. 1 is odd, so the sign would change from negative to positive. Our constant term, our number without a variable, the sign's not going to do anything because there is not a variable there. Questions on how we got to this here? So if the exponent is odd, change the sign. If the exponent's even, keep the sign the same. Now, after we do this, we can count the number of sign changes. X to the fifth, x to the fourth. We're going from negative to negative. Our next one's going from negative to negative. It doesn't change. Next one is negative to negative. One after that is going from negative to positive. So we have 1. Last one, positive to positive, so no. So the number of negatives that we can have is 1, or less than it by an even amount. Well, if we try to take 2 away from 1, we get negative 1. So the only possible solutions that we have for this here is 1 negative. Positive, negative, complex. Now what this table is doing is setting up every single possible case that we can have with positive, negative, and complex zeros. How many different arrangements did we have for the positives? 3, 2, 4, and 0. And negatives we have 1, yes? And what we're doing with this table is really linking every combination of these two together. And I always start with the most. 4 positive and 1 negative. Now we said the degree for this is what? 5, yes? In both cases, the degree is 5. The biggest exponent is 5, which tells us the number of solutions we should have is 5, yes? If I have 4 positive solutions and 1 negative, we have a total of 5. If we had that setup, would we have every solution? Well, yeah, because we have all 5, yes? So that tells us the number of complex for that would be 0, because every solution is accounted for. Now the way I would do this next would take 2 of the solutions, because with negative or positive we can have whatever that amount is or less than it by an even amount. Can I take 2 away from our 1 in the negative column? Well, no, because if we do, we'd have negative 1. It doesn't work. So what I do instead, since that's really for here is going to say 1, I would take 2 away from the positives. If I take 2 away from 4, I have 2. The most negatives we can have is 1. In all cases for this one here is going to be 1. And let's see how many we have. 2 positives, 1 negatives gives us a total of 3 solutions. How many do we need? So how many are we missing? That means we have 2 complex. Now with having 2 positives, I would assign it with every possible negative combination, but here we only have 1. So I can't change that, but I can still take 2 away from the positives, giving us 0, 1. If I have 0 positives and 1 negative, we have a total of how many zeros? 1. How many are we missing? Because we need it to be 5. So if we have 0 positives and 1 negative, we're going to have 4 complex. Questions on this here? Questions on anything we've done so far? Okay. If we do have time, we'll come back to 28. If not, the second hour's video does have it. Last set is solving. Every single problem that will be on the test with solving will give you enough solutions to get you down to a quadratic, if not give them all to you. So 29 through 34, is there one of those in particular you want to look at first? Now with every single solving problem on the test, the first thing you should do every single time is graph it. So if we look at 29, the first thing, especially when it says solve, is plug it into the graphing calculator. So we're going to have x to the 5th minus 20x to the 3rd plus 20x squared minus 21x plus 20. Graph. We see here it crosses the graph in 3 places. Now to see those, we can go second graph. And again, when we're looking for solutions, we're looking for what values of x will make the y value be 0. We're more focused on what values of x will make the y be 0. So y is 0 for here in 3 spots, -5, 1, and 4. -5, 1, and 4 are the 3 of the solutions. Now for this here, the degree is 5, so there should be 5 solutions. So that means we're missing 2. So if a problem of a degree 5 showed up on the test, you will be able to graph and get at least 3. It might give you 4, it might give you all 5, but it will give you at least 2 less than the degree. Now the first one we can do for this here is 1. And do synthetic division, because we need to do synthetic division to decrease the degree from degree 5 down to degree 4. We'll do it again to go from 4 to 3, and we'll do it one more time to go from 3 to 2. So we'll put 1 in the cubby hole. Going across the top, we have 1 for x to the 5th. Yes. Since we don't have an x to the 4th term, we'll fill it in as 0. Our x to the 3rd term will be -20. Our x squared term is going to be 20. Our x term is -21. And our last term is 20. We'll bring down the 1. Now we're going to do our multiplication add. We're going to do synthetic division. So we're going to do 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. -20 plus 1 is -19. 1 times -19 is -19. 20 plus -19 is 1 times 1 is 1. -21 plus 1 is -20. And 1 times -20 is -20. And 20 plus -20 is 0. Now, unless we know one of the solutions definitely repeated, I would go on and try the rest of the solutions I found first, and then go back to repeated solutions last. So we can do the same thing with 4. 4 times our 1 is 4. 1 plus 4 is 5. 4 times our 5 is 20. Negative 19 plus 20 is 1. 4 times 1 is 4. 1 plus 4 is 5. And 4 times 5 is 20. And then negative 20 plus 20 is indeed 0. Yes. So now we're down to a degree 3. Let's do this one more time. And if we do this one more time, we will get to a degree 2. And we can solve from there. Negative 5 times 1 is negative 5. 5 plus negative 5 is 0. Negative 5 times 0 is 0. 1 plus 0 is 1. Negative 5 times 1 is negative 5, and 5 plus negative 5 is 0. And again, when solving these here, especially if it's already told us, the graphing calculator has told us it is a solution, we know the remainder will have to be 0 for each of these synthetic divisions. Now at this point here, we can put the remainders back in, or not the remainders, of variables. So we'd have r, 1 is our term without x, 0 is our term with x, and our other 1 is our term with x squared. So what we have left is that x squared plus 1 is equal to 0. If you don't have a middle term, we can solve by the square root method. We're going to get x squared by itself first, so we would subtract 1 from both sides, telling us x squared is negative 1. At this point here, we can take the square root of both sides, telling us x is equal to plus or minus square root of negative 1. Well, the negative is going to come out as I, and the square root of 1 is 1. So we would have 1i, or just I. Well, by definition, the square root of negative 1 is I. That's what I is. So our solutions are plus or minus I, negative 5, 1, and 4. Because I, we have positive I and negative I. That's 2 solutions. Negative 5, 1, and 4, giving us a total of 5. We have found all 5 solutions. So we are finished. We found them all. Questions on this here? Questions on anything we've done so far? Is there another one we want to see with solving? $33? Yeah, we can do 33. 3x cubed plus x squared minus 38x plus 24. Again, with this here, the first thing I would do is graph it. Type the whole thing into the graphing calculator and hit graph. And then we can look at the table. So it tells us that 2 of the solutions, 2 of the values of x that make the y value be 0 or make it equal 0 are negative 4 and 3. Yes? So here we can say x is equal to negative 4 and x is equal to 3. Since this is a degree 3, how many solutions should we have? 3, because whatever the degree is the same as the number of solutions. So all we're missing is 1. We need 1 more. Well, at this point here, we can go on and do synthetic division and solve for the remaining 0. And luckily, it's going to be pretty nice solving for the last one. Do we want to do synthetic division with negative 4 or 3 first? Y'all pick negative 4. And we'll do the process with this here. So we'll say negative 4 times 3 is negative 12. Negative 1 plus, or 1 plus negative 12 is negative 11. negative 4 times negative 11 is going to be positive 44. Negative 38 plus 44 is positive 6. And negative 4 times 6 is negative 24, giving us 0. So we've reduced the degree from a degree 3 down to a degree 2. It is a quadratic. We could solve by the quadratic equation at this point, but we do have another solution given to us by graphing, and we're going to go on and use it. It's going to make it easier to solve for the last one if we do one more synthetic division. Here, our 3 times 3 is 9. Negative 11 plus 9 is negative 2. 3 times negative 2 is negative 6. And 6 plus negative 6 is 0. At this point in, we'll fill the variables back in. Our 0 in the box is the remainder. Our negative 2 is our constant. 3 is our term with x. So what we have left, the equation we have left to solve for x is 3x minus 2 is equal to 0. Since we don't have any powers, any exponents left, all we got to do is get x by itself. And the first thing we can do is add 2 to both sides, telling us 3x is equal to 2. And the last thing we need to do is divide both sides by 3, telling us x is 2/3. So our solution for this here is negative 4, 3, and 2/3. Any other questions on 33 through 34? We good with 29 through 34? Are we good with all these here? Or is there one you want to look at? We good? Or is there one? Okay. Do we want to look at back at 28 for possible positive and negative and complex solutions? Okay. This here. So to find the number of positive solutions, we count the number of sign changes. Now for positive, negative, and complex solutions, Descartes' rule of signs, we do not have to plug any missing variables back in. So we can just count them as they are. Our first one's going from positive to negative, so that's 1. Then we go from negative to positive, which is 2. Our next one goes from positive to negative, which is 3. Then we go from negative to negative, so that doesn't count. Our next one goes from negative to positive, making 4. And the last one goes from positive to negative, giving us 5. So for our positives, the most we can have is 5 or less than it by an even amount. So we could have 5, 3, or 1. We can't go any lower than that because if we take 2 away again, we'd have negatives, so that doesn't work. Now to look at the negative case, we're taking g of negative x. And again, if the exponent is odd, change the sign. If the exponent is even, keep it. So our first one is 6x to the 7th. Is the exponent even or odd? Odd, so we change it from positive to negative. Our next one is 5x to the 5th. Is the 5th power even or odd? Odd, so we change it from negative to positive. Our one after that is 27x to the 4th. Is the exponent even or odd? Even, so the sign stays the same. Our next one is 30x cubed. 30x to the 3rd. It is odd, so it would change from negative to positive. Our one after that is 20x squared. Our exponent is even, so the sign would stay the same. Our next one, 5x, is really to the first power, so that's odd. So that means we change it. And our number without a variable, we don't do anything to. And again, at this point, we're going to count the number of sign changes. So our first one's negative to positive, which would be 1. Next one's positive to positive, so no. Next one's positive to positive, so that's not a sign change. Our next one's positive to negative, so that will be our second. Negative to negative, so no. And lastly, negative to negative, so no. So the most negatives we can have is 2, or less than it by an even amount, which would be 0, and we can't go lower than that. So we have 5, 3, 1, 2, 0. Now we're going to set up our table, positive, negative, and complex. And we always start out with the most positives and most negatives, 5 and 2. Now the degree for this is what? Degree for this, biggest exponent. 7. So the number of solutions should always be 7. If we have 5 positives and 2 negatives, that gives us a total of how many? 5 plus 2. Do we have all 7 solutions? So that means the number of complex is 0. Now, what I do for these here to make sure I have every combination is I subtract 2 from the negatives till I can't anymore. And whenever I get to that point, we reset it and take 2 away from the positives and repeat the process. So can we take 2 away from our negatives, which is 2? Well, yes, 2 minus 2 is 0. So I can have 5 positives and 0 negatives. Well, how many solutions is that? 5. We need it to be 7, so we're missing how many? 2. Can I take 2 away from the negatives again? Well, no, the only 2 options are 2 and 0, yes? So I reset it back to 2 and take 2 away from the positives. Telling us we can have 3 positives and 2 negatives, which gives us a total of 5 solutions. We need it to be 7. We're missing 2, and they would be complex. Now this, we can take 2 away from the negatives again, giving us 0. And that we have 3 positives and 0 negatives, which gives us how many solutions? 3. How many are we missing? 4. So our next option is that we have 3 positive, 0 negative, and 4 complex. Can I take 2 away from the negatives now? Well, no, it's back to 0, yes? So I reset it back to and take 2 away from the positives, which gives us 1. So we have 1 positive, 2 negative, which is a total of, how many do we need? 7, yes? So we're missing 4. We take 2 away from the negatives again, telling us that we have 1 positive, 0 negatives. Well, that's a total of how many solutions? How many are we missing? Because each of these should total 7. As our first one, 5 plus 2 is 7. So we're good there. Well, 5 plus 2 plus 0 is 7. Our next one, 5 plus 0 plus 2 is 7. Our next one, 3 plus 2 is 5 plus 2 is 7. One after that, 3 plus 0 plus 4 is 7. The next one, 1 plus 2 is 3 plus 4 is 7. Last one, 1 plus 0 is 1 plus 6 is 7. And this here is our final answer. So again, go back through. If there's anything you're still a little fuzzy with, go back over it, ask questions if you need to. But we are starting this test tomorrow. You should or can finish this test in one day. So go through, refresh back up on anything that you might not be clear with, so you're ready for tomorrow. Um,